1.1.3 Evaluating Combinations. One of our goals in this chapter is to isolate issues about thinking procedurally. As case in point, let us consider that in evaluating combinations, the interpreter is itself following a procedure. To evaluate a combination, do the following. 1. Evaluate the sub-expressions of the combination. 2. Apply the procedure that is the value of the leftmost sub-expression, the operator, to the arguments that are the values of the other sub-expressions, the operands. Even this simple rule illustrates some important points about the process in general. First, observe that the first step dictates that in order to accomplish the evaluation process for a combination, we must first perform the evaluation process on each element of the combination. Thus, the evaluation rule is recursive in nature. That is, it includes as one of the steps the need to invoke the rule itself. Notice how succinctly the idea of recursion can be used to express what, in the case of deeply nested combination, would otherwise be viewed as a rather complicated process. For example, evaluating, and then I'm going to go ahead and do this. This expression here requires the evaluation rule be applied to 4 different combinations. You can obtain a picture of this combination process by representing the combination in the form as a tree as shown in figure 1.1. So here's what I do. So we do all the interior ones and then we work out just like you do normally. So I've got this here set up so we can see kind of what it does. So 4 and 6 ends up being 24. And then 2 and 24 ends up being 26. And then over here, 3 and 7 is 10, and 5 is 15. Wait, 7, 8, 9, 10, yep, 15. And then last but not least, we do 26 and 15, which I'm going to do by hand because I know I'm just going to mess it up. Just because I know I am. So ends up being 11 and 3, 4. Oh, multiply, that's why. Multiplying 26 and 15, that's why it's... See, this is why you pay attention. Okay, so now 26 times 15. You know what, let's let this guy do it. So, multiply 26 and 15. Better make sure we go back and put a space, otherwise it won't work. And 15. And we get 390, which is going to go in our top slot here. Okay, so 390 should be what we get. You can kind of see how it branched out here. Each combination is represented by a node with branches corresponding to the operator and operands of the combination stemming from it. The terminal nodes, that is, the nodes with no branches stemming from them, represent either operators or numbers. Viewing the evaluation in terms of a tree, we can imagine that the values of the operands percolate upwards, starting from the terminal nodes and then combining at higher and higher levels. In general, we shall see that recursion is a very powerful technique for dealing with hierarchical, tree-like objects. In fact, the percolate values upward form of the evaluation rule is an important example of a general kind of process known as tree accumulation. Figure 1.1 showing the value of each subcombination. So you can see we had 3, 5, and 7, got 15. We had multiplied 4 and 6, got 24. Added 2 to it, got 26. Multiplied both of those and ended up with 390. Next, observe that the repeated application of the first step brings us to the point where we need to evaluate not combinations, but primitive expressions such as numerals, built-in operators, or other names. We take care of the primitive cases by stipulating that the values of the numerals are the numbers that they name. The values of built-in operators are the machine instruction sequences that carry out the corresponding operations, and the values of the other names are the objects associated with those names in the environment. We may regard the second rule as a special case of the third one, by stipulating that symbols such as add and multiply are also included in the global environment, and are associated with sequences of machine instructions that are at their values. The key point to notice is the role of the environment in determining the meaning of the symbols and expressions. In an interactive language such as Lisp, it is meaningless to speak of the value of an expression plus, such as parenthesis, plus x and 1, parenthesis, without specifying any information about the environment that would provide a meaning for the symbol x, or even for the symbol plus. As we shall see in Chapter 3, the general notion of the environment as providing a context in which the evaluation takes place will play an important role in our understanding of program execution. Notice the evaluation rule given above does not handle definitions. For instance, evaluating define x as 3 does not apply define to two arguments, one of which the value is the symbol of x and the other is which is 3, since the purpose of define is precisely to associate x with a value, that is, define x as 3 is not a combination. Such exceptions to the general evaluation rule are called special forms. Define is the only example of a special form that we have seen so far, but we will meet others shortly. Each special form has its own evaluation rule. The various kinds of expressions, each with its associated evaluation rule, constitute the syntax of the programming language. In comparison with most other programming languages, Lisp has a very simple syntax. That is, the evaluation rule for expressions can be described by a simple general rule together with specialized rules for a small number of special forms.